Yes.
A reminder to ask about visitors.
Yes.
Because I would announce Potini Okanovu and B.L. Unger, who doesn't yet seem to be here. Potini's giving the Astro Seminar tomorrow, and they'll both be here for the week.
Great. Are there any other visitors? Quiet morning. Any other visitors today? All right. I already pressed record. Today we're pleased to have one of our postdocs, Anirban Roy, here to tell us about
line intensity mapping.
Line intensity mapping.
That's kind of a strong.
Sorry, I'm gonna. No, I'm operating in a very limited capacity today.
Survived a week-long school break. I wonder.
I think I just froze this.
Oh.
You should go on.
Yeah. Can I have some chalks?
Is there no chalk?
No.
That's hilarious.
Oh, I can bring some.
I have chalk.
Oh, there's a pink chalk, if that's of any use to you.
Use it. Can I start now?
Yeah, go ahead and start.
So thank you very much, Mike, for asking me to present what I'm currently working now. Probably most of you don't know me, so just let me introduce myself. I'm Anirban Roy. I'm a new postdoc here. I mean, not very new, but I came here in October. I'm working with Professor Anthony Pullen. And during my PhD, I was working on the secondary CMB anisotropy, mainly induced by thermal synapse enthalpy effect and lensing, and also some other weird signal, particularly the secondary remote signal from patchy ionization, and we have to see that it can contaminate the primary remote or not. And then I moved to Cornell as a postdoc, and there Cornell is involved in CCAT Prime telescope, which aim to probe the line intensity mapping. And then last 2-3 years, I'm working on multi-line intensity mapping, so I'll talk briefly about it. And feel free to ask me anything. And also, this is my first time Blackboard talk, so I'm a little bit excited. Let's see. So, if I'm asked to name one parameter related to the galaxy formation, and that is very important, then I will say that that will be star formation rate for me. It basically tells us that what is the total amount of stars formed in a galaxy. Just to give you some intuition that if I consider a Milky Way-like galaxy, it will be like, it's debatable, but it's like 0.16 plus minus 0.2 or so on. It depends on how you are modeling and all those things. The way we estimate star formation rate by...
For non-experts, you should tell the units.
Oh, sorry. Here. So it's like total number of stars that forms every year. It's a very, so it can change actually. So it can be plus minus 2 if you consider only the Herschel-like observations. If you consider multi-wavelength observation, then it can be 0.16 plus minus. Now the question is that why it is important? Because the star formation rate is a very complex quantity. It captures how the merger history of dark matter halos, the accretion rate, turbulence inside the galaxies, and then if you go more and more, you want to make it more complex, the turbulence and also the cooling processes. Now I can make it a little bit more complicated by adding one extra variable here. Now I am not interested at each galaxies that how they are forming stars, but rather I want to probe the star formation history across the redshift. It is particularly important because if I consider QZ limits, for example, if it is say this around 10 to 20, you can consider that the first generation of stars and galaxies were formed, and before that it was kind of sea of neutral hydrogen. And once the first generation of stars and galaxies were formed, they produced the ultraviolet photons, and those photons interact with the neutral hydrogen, and the universe started to become ionized. Then I can consider another limit, which is Z is around between 5.5 to 6. When the ionization ended, based on the current data set, there are different data sets. For example, the tau constant from Planck, the damping of Lyman alpha forest, the quasar near Jones observation, and so on. Then if I go around 1.9, we can observe that transformation rate peaks, the density peaks around that redshift, and after that it declines. And we don't understand very well what it happens. It is what we observe, but we don't know. So we need a probe that can kind of probe the star formation rate history across a broad redshift range so that we can understand better about the physical processes. Now, there should be a new probe that can satisfy a few conditions. One is that new probe should be related to the star formation rate or depend on the star formation rate. Second thing, it should be able to do the tomography of the universe so that I can capture the jet evolution. So it should be third thing is that also, as we are probing the large scale structure, this probe should be able to give us the cosmological information. And last but not the least, it should be relatively cheaper.
Meaning possible.
Possible. So just to give you an estimate, just to start from this point, that one typical line intensity mapping experiments like CCAT, they cost around $50 to $70 million. So
on the high end. On the high end.
On high end, yeah, exactly. And but more interesting than that, you can typically transform all the CMB experiments into line intensity mapping experiments. So if you are more interested to observe the cosmic microwave background once the operation is ended, and as you have more data on the atmospheres and the site, and you have already the elevators and everything, just you can add one spectrometer and you can have your line intensity mapping experiment. So it's much cheaper than.
What's the role of the cosmological information here? That's another thing you want out of your observing.
I'm
it's
going
not
to talk
related.
about mainly these two things: astrophysics and cosmological information.
I see. So yeah, okay.
So as line intensity mapping is probing the universe in a tomographic way, I want to understand the cosmology at different redshift. So that's the ultimate goal, and I'll talk in detail. Now, second thing is that how does it help to do tomography? So for example, if I just plot new observation, here I can change redshift and new ops. So for a particular line, it's just new observation is new redshift frequency divided by 1 plus z. So if I choose an observational frequency like this, I can probe the universe at this redshift. Now if I change the observational frequency of my experiment to another frequency, I observe the universe at
The implication here is that you're going to use a line. So
this is only for
specific,
one
yeah.
line. So yeah, I was going back. So now it can be any line.
Right.
But I'm particularly going to talk about several lines except 21 centimeter line. So 21 centimeter mapping is also a line, but that field has evolved quite significantly. So here, when I talk about multi-line intensity mapping, I'm particularly talking about C2, singular ionized, which is 58 micrometers.
You know, there's a shadow that makes it a little hard. If you had a different chunk that was darker maybe, or did it out of the shadow.
So C2, 58 micrometer, I always remember a frequency limit, so it will be around 1900 gigahertz. Then we are talking about CO 10 to CO. You can go up to 13, 12 or so on. This frequency is 115. And you can also do oxygen 3 if you're lucky, but oxygen 3, which is 3.00 gigahertz. So when I'm talking about multi-line intensity mapping, I'm basically talking about different lines, atomic and molecular lines, that have different reference frequencies. And that is very interesting because then we can have several lines, and by changing the observational frequency, I can probe the universe at different epochs. And that is the one of the interesting property of this. So it can do the tomography of the universe. Now let me talk about how do you want to extract the astrophysical properties. So what we generally do, we can use the galaxy surface to understand that how galaxies are distributed. So for example, if I have a map of galaxies, it is basically giving me the cosmological information. For example, sigma 8, omega m, and so on. Now the question is, what I'll observe if we have a line intensity mapping experiment. What I'm basically going to see something like this. I cannot probe the individual galaxies here, but rather I'm observing the integrated emission emitted from all the galaxies. But even if you see by eyes, you can understand that these are correlated somehow. Where I have more galaxies, I have the line intensity, the intensity is much higher. And if these are voids, I not get any intensity. That is the fun fact about line intensity mapping. I don't need to resolve each galaxy, rather I can observe the total intensity coming from those galaxies. Now the biggest question is, how do I go from this map to that map? And in my opinion, there is the most uncertain part, that how do I take care all the astrophysical information to go from this map to that map?
You mean if you were doing a prediction,
Or
right? You had some simulation, you had some galaxies. How would you know how they emitted in these particular lines? Is that what you mean?
Yeah, exactly. Because ultimately we want to observe this kind of map, right? Now the question is, okay, if I observe a line intensity map at a particular redshift, let's say Z, what I'm going to learn from it. So I need to know that how I can do the forward modeling so that I can interpret the signal when it will be ultimately observed. And all the line intensity mapping observations are trying to probe this and to understand that how the map will look like. Of course, we don't do it at the map level, but we also see the power spectrum, which I'm going to talk in a second. So,
could you give us an idea, given the sort of present experiments of landlines, what's the angular resolution in the line intensity mapping?
So I am involved at CCPP Prime Telescope. It depends on which.
Could you just write the name of that up there? I don't think I'm hearing it well.
It is called Chiro Chayantor Atacama Telescope. It's near Alma. And the resolution, so it has the frequency range 220 gigahertz to 4110. If I want to observe C2, that will cover the redshift range 3.6 to 7.8 for the C2. And the resolution at 220 gigahertz, it is around I guess 33 arc second, and at 4110 it is 57, something like that.
So it's super nice question. So to understand what you say, you have some modeling, and then you want to see how you go from the left to the right in order because of the right is what you see. You mean like models of structure formation, like clustering things, or the profiling in depth in the
Both.
In the city?
Both. So we are
it's quite sensitive, the same kind of to both things.
Yeah, so the clustering property is pretty straightforward because we know the underlying cosmology, we know the sigma 8 parameters, and if we use an in-body simulation, I can I can create the Hello catalog or whatever, like from TNG or universe machine or any body simulation code. The question is, how do I model from the cluster, the Hello catalog to the line intensity? And there I have influence of astrophysics. And that is the main uncertain part in this whole section. Now, to model the line intensity for a particular Hello catalog, what we typically do, we assume that the line luminosities are related to the star formation rate, which I started, and it can sort of behave like a power law. So I can relate it with the equation like something like log L is equal to alpha log SFR plus beta, which is kind of telling me that what will be the slope and the cutoff. Now, of course, the galaxies don't follow a particular line like this. Galaxies are not well here. So you can have also scatter on top of it. So you have a range, and you also capture the uncertainty between this log L and SFR. And that is what we observe from the targeted observations, for example, the ALMA-like surface. So if we observe each galaxies and I want to measure that what is the line luminosity for a particular line, that can be C2, CO102, CO1312, and also I relate it with the star formation rate, I usually get this kind of relation.
Does ALMA have observations in this range of these lines
So ALMA is observations at low redshift.
at low redshift?
So
Okay.
we know how the scaling relation will be at low redshift. But the question is, how the high redshift galaxies, do they behave like ALMA-like scaling relations, or do they behave very differently? And that is what we ultimately want to concentrate.
And for C2, I guess CO is you're looking at the surfaces of molecular clouds or something. But for C2, where is the C2 emitted? Like, what emits the C2?
Okay, that's...
No one knows.
Patrick's laughing. Okay.
Like, yeah.
Isn't it the loudest line in the whole
Yes.
spectrum? And we don't understand it? Oh my God. This is why we're spectroscopists.
And that's why you want to model. That's why just line intensity mapping is important.
So they're
Just
like, it's not like you can look with ALMA at some like very nearby thing and you see it's like in the diffuse.
It either is dominated by the diffuse gas, the dense gas, or the intermediate gas.
But other than that, it's
But
all
it's not
locked
coming
down.
from the stars.
It's not coming from the stars.
Okay, good.
But also, if you go at high redshift, beyond redshift 6, then deionization happens. So the gas are pushed away. Those like the C2 are probably they're floating in the sea of hydrogen, neutral hydrogen atoms. So that becomes much more complicated if I go at high redshift. So I'm going to talk about that also.
But it is interesting. So you're saying that they model it like the kind of goal is to see a relationship like this. But of course, there's other numbers other than star formation rate you probably want in there, like the dust to gas ratio, the metallicity of the gas, and things like that. Must all be in there. But are people thinking SFR because there's an understanding of SFR for these
I
objects?
think it is observationally motivated because we observe it, but people have modified this equation in terms of metallicity.
Yeah.
And now we are kind of debating that is it the star formation rate is the base treasure of line luminosities or not? It can happen that it may be the M star, the total number of stars, the mass of the new stars, that is probably strongly correlated with the log L. And I am not an expert in that modeling, I work mostly on the cosmology, so we kind of take it for granted that, okay, let me first model it, then we'll see that what are the observational challenges and so on.
I'm disappointed here. I understand that you measure L in this graph that you drew there. How do you measure the star formation rate?
So star formation rate you usually measure using multi-wavelength observation. For example, multi-wavelength observation, usually in UV you can observe them, and then you have to consider an initial mass function. And then from the initial mass function, you can understand that how many stars are forming. Also, why multi-wavelength observation is important, because some of the young stars, which are very dusty, they absorb those UV radiation, and radiated in IR. So when I observe a particular galaxy in both UV plus IR, I can kind of relate it with the star formation rate, because new stars are dusty and they are emitting in IR, and also the massive and short-lived stars they are emitting in UV. So adding all these pieces, you can get some estimate on star formation rate. Now, coming back to the point that our aim is to ultimately observe some of the maps, which we are planning to, we aim to observe. But the question is that what we are going to observe. Are we going to observe a map, and then we have to analyze that what are the physical processes take place to make this map. And once, usually when a cosmologist sees a map, what we really want to do, we want to calculate the statistical properties under Gaussian approximation, which is calculating the power spectra. So once we have this map, I can calculate the power spectra on this map, which will look something like that. So this is PK. This shape and the amplitude of the power spectra is very important, because this flat shape of the power spectra is the short noise dominated, and this is the clustering properties. It can be related to the cosmological matter power spectra, something like EK line is equal to E square. So B is the bias parameter, which basically tells that what will be the amplitude here. So if I consider different models, if I change this parameter, the values of alpha and beta, the shape of the clustering properties will change, and it is proportional to the matter power spectra. And P short is the flat noise, and just to give you an idea that what is short noise, for example, if I have an iPhone and I go to a dark room and I want to take a picture of that dark place or whatever dark region, I'll expect that if I use my camera, the picture will be completely dark. But actually what we see something like this with some random noises, which is a little bit greenish. It depends on how sensitive your camera is. The reason is this is the short noise term what we observe, because there are less number of photons, so the Poisson noise increases. So as we are going to the small scales, there are not many galaxies, so what I am left out of, that is the short noise term. Now the main question is that what will be the amplitude of this power spectra, because that strongly depends on.
So the shot noise is the Poisson contribution of the galaxies, or it's the noise contribution of the instrument? It's
no.
It's just from the
Just
galaxies.
from the galaxies.
Okay.
It's just a simple galaxy surface is the same. Now I'll come back to the instrumental noise, because I want to see that what is the detectability probability of this line intensity power spectra by a particular experiment. If I have an experiment which has the instrumental white noise power spectra is something like this, is what I'm going to actually observe here. I'll have, if I be in the power spectrum, I'll observe something like this. When I'm adding just instrumental noise into it, but in reality it doesn't work like this, because instrument they have also the beam size, so at small scale there is beam smearing effect, so I don't see, so ultimately I see something like this, which is exponential. Now if I include all the effects, the interesting thing is that how well I can measure this power spectra. So in my first paper, which is Roy et al. 2023, we tried to write a code which is known as LIMPy, line intensity mapping in Python, where I included different models, different star formation rate, different line luminosity relations, we put all together just to predict that what will be the amplitude of the power spectra and the shape of the power spectra. which is not probably very interesting because it's just nothing new. It's just putting everything all together just to see that how well I can understand this behavior and what will be the detectability probability of the signal if I have a particular line intensity mapping experiment.
Quick question.
Yeah.
What's the transition scale K, like the typical number you have in mind?
It depends at which redshift I'm probing, but you can kind of safely understand K is equal to 1, around 1. It's between 0.5 to 1. Depends on which redshift I'm
The
probing.
usual inverse mega per second.
Yeah, exactly. It's very basic. So, any other questions? Okay. So yeah, when I wrote this paper and when I was considering only the instrumental noise, and for the optimistic model and pessimistic model, the signal to noise ratio was few of tens to few hundreds. But this is a very high, very high number, but probably in reality it is not going to happen. So now I'm going to talk about that what are the challenges that can affect this measurement and how are we going to tackle those challenges. So there are mainly, of course, the instrumental noise is very important. If I have more money, I can have more detectors, and I sense the instrumental sensitivity of the instrumental noise can go down. And that is kind of, let's say, under our control. Also, it depends that at which generation experiments we are trying to probe. For example, in CMB-like experiments, we are now in third generation experiments, but in future we are looking for CMBS4-like experiments where we have unprecedented sensitivity to measure some of the new physics. But here we are into the first generation experiments. So as time progresses, that we expect that the instrumental noise will go down like Moore's law. Now, just to talk about the challenges, I can go here. So, if you draw that plot again. So let's say this is the C2 line, and if I have an observational frequency, I'm gonna observe this redshift, and that is my target. But C2 is not the only line that can come into my telescope. There can be other lines that can be redshifted to this observational frequency. For example, if it is, let's say, CO43, the CO43 will be also redshifted to these new observations, and what I am going to ultimately observe, that is a superposition of these two signals. So C2 will come from Z1 and CO43 will come from the redshift Z2. And there can be many different CO lines from low redshift, so all will be mixed up. And we call these undesired lines interlopers. And the one big challenge is that how we are gonna get rid of these interlopers. Another thing is that we don't observe just the lines, but also we observe the continuum emission. So if I have something like flux, I observe something like and we don't know basically that what will be the amplitude of this continuum. And that is mainly coming from the dusty galaxies, for example, CIB and so on. We know how to tackle CIB a little bit in a better way because we know how to do the component separation, and we can kind of from simulations, we can understand. Now, one thing is to apply the principal component separation and just to understand that what are the modes that is influencing the continuum emission. But another thing is that interlopers. So we wrote another paper recently, like just 2 months ago, Roy and Natalia. Where we talked about that using the cross correlation effect or the cross correlation between two lines to get rid of interlopers. The way it works, for example, if I have total signal P total is equal to P line 1, P line 1 from a particular redshift jet plus instrumental noise plus P interloper from different redshift. Now, if I have another frequency channel, let's say here, so I can, as these two lines are coming from the same redshift Z1, but I am observing these two lines by using two different frequency channels. But they are actually coming essentially from the same underlying sources. Now, they might have different interlopers here and here, but the underlying signal that I'm trying to probe, they are coming from the same redshift. And that is, I'm going to write here in the equation form. So ultimately, I'm observing through one frequency channel, the line 1 from a particular redshift jet, plus instrumental noise, plus interloper. Those are coming from different redshifts, Z1, Z2, Z3, and so on. I have another line, which is this one, which is actually coming from the same redshift. I am writing it L2, the line 2, from the same redshift. That is the important thing. And then I have different instrumental noise because I am considering another frequency channel. And the interlopers, those are coming from different redshifts. These are not related because they have different redshift frequencies. Now the idea is, what if I cross-correlate these two things that I ultimately observe? The assumption is that these interloper, as they are coming from different redshifts, Z1, Z2, Z3, and Z1 prime, Z2 prime, and Z3 prime, they will not correlate with each other. Noise will not also correlate with each other, but we also know how to take care of instrumental noise in a better way at the data analysis level. Now, if I cross-correlate these two things, I expect this signal, as they are coming from the same sources, they will correlate with each other, and other stuff will not correlate with each other as they are coming from different sources. And that was the idea of this paper. And what we have found, that if we have optimistic models, one can always question about that, okay, how bright your galaxies are. What models did you choose for the star formation rate and spectral? So this is completely unknown thing. So we consider several models, and what we have found at each cases, the bias of measurement decreases. So I am going to probe the more unbiased measurement. Just to tell you that ultimately, if I have the signal is here, which is like this is the line intensity mapping signal, and if I add some interlopers, when I add these two things, I'll ultimately observe something like this. And ultimate goal is to get this map, signal only map, from this total map. And that is a very tricky thing to do because it might be swamped by the interlopers only. But when we want to do the tomography, I want to know that how the universe behaved at that particular redshift, not at the total map level.
Sorry, so you were just talking about characterizing the power spectra, but now are you changing the goalpost? You're saying you actually do want to map.
Yes.
And is that what I'm meant to?
Yes, like it is always at the map level analysis, then we go to the power spectra. But just to do the analysis that it works at the power spectral level or not, first we simulated different
see.
maps, and
Okay.
then we analyzed
Okay.
it at the map level just to check the fidelity.
Okay,
of
but it's
the-
not that in the observations, you think you're gonna recover that map on the left, to the left of the plus sign,
Yeah.
or not from
Maybe
current
it will be
experiments?
residual noise and interloper dominated.
Okay.
Not sure. So
Oh,
it
okay,
depends on the
okay,
how
okay,
observed, how lucky we are basically.
Got it.
If the model is brighter, we might get see something like, which might look like some of the models that can predict the signal, but if
Okay.
the models are not that great, then you can just see the noise, residual noise at the local signal.
I have a quick question. So for the last two terms, like they primarily come from the same object. So won't you expect some?
No, they are coming from different objects. So that's why I have written the Z1, Z2, Z3, and these are Z1 prime, Z2 prime, and Z3. So they
Right.
are not coming.
I just mean like by primordially, I mean really from very, very early universe. Like there's some.
No, these are at the late time universe. So
So you're saying like the late time processing is so different that the primordial information is sort of lost in some sense. Like,
no, all of the power spectra of the interloper, you can relate it with the primordial power spectra by this equation. So if you have the primordial, so this PM is the matter power spectra, which is dark matter only power spectra. Now, if you add astrophysical phenomena with it, then you get the line intensity mapping power spectra, and that line intensity mapping power spectra you are generating at several redshift. Now, if you are to observe one particular line from this redshift, there are other interlopers which are technically related to this primordial power spectra, but added with some astrophysical complex phenomena. So ultimately, I am adding some extra terms which I don't want, because I want to observe the universe at this particular redshift.
oh, okay. So that's the separation you have done in the plan
Exactly,
already.
exactly. So, and ultimately what we have found that we lose little bit signal to noise ratio, because the cross power spectra, when you calculate the cross power spectra between two lines, so if I have power spectra for line 1, the same problem. Yes. Okay. So if I have line 1 and line 2 power spectra, if I calculate the cross power spectra, it will be something like this. So the thing is that I'm losing some signal, but also I want to probe the unbiased signal. So if we have the competitions between two, but we have proposed that, yeah, we are losing signal to noise ratio significantly, but we are going to probe the unbiased signal. So that is the kind of the aim of this paper. Let me see how much time I have. So another thing is that what do you want to learn from this line intensity mapping observations? For example, any limit will be interesting because we can rule out some of the models. For example, that now we don't know that how this power spectra will look like at high redshift. But if we have some limit like this, we can actually rule out some of the models, and that will be interesting thing to do. Another thing is that what we know about reionization epoch, which is kind of not well explored. And there we are working with Anthony just to understand that how these line emissions will be correlated with the 21 centimeter signal. So just to give you a sense that if the reionization epoch happened for 50%, let's say around z is equal to 7, what I'll observe some ionized bubbles, and other stuff will be neutral. And these ionized bubbles will form where I have the sources, galaxies. So those galaxies will form the UV, produce the UV photons, and they will interact with the neutral hydrogen, and the universe will be ionized. They usually form the ionized bubbles, and as time passes, they merge with each other and makes the universe ionized. But this C2, CO, or whatever line emission, they're coming from the halo. So the question is that if I have a 21 centimeter map, I'll observe the signal from this region, except where I have the ionized bubbles. So if I cross correlate these two maps, what I'll anticipate that 21 C2, I'll get something like anti-correlation. The reason is that where I have 21 centimeter signal, I don't have the C2, and at the scales where I have the line intensity mapping signal, I will not have neutral hydrogen. And this signal is very interesting in a sense that we can do tomography with it. Because at some point, if I go at high redshift, let's say z is equal to 9, probably universe was x is equal to 0.1. So maybe 10% of universe was ionized. Then the signal will behave in a different way. The amplitude will be low. But as time passes, the universe becomes more and more ionized, and I'll get the maximum anti-correlation when the universe is half and half ionized and neutral, because then the variance of this power spectrum, the variance will be the highest. And then as the universe becomes more and more ionized, this will again go up, so that, and when the universe is completely ionized, this will be, the correlation will be 0, because there is no 21 centimeter signal. What we are trying to prove that if we have an experiment like SKA or 21, which is very futuristic, but we just use their noise properties, and if I have a CCAT like C2 experiment, if I cross correlate these two things, can I prove this signal or not?
So
yeah.
I haven't really thought about this too much, but at the centers of each of those bubbles, there's like a galactic disk, which is neutral hydrogen rich, right? Like there'd be a DLA there or something. And it's not a lot, it must be a small fraction of the total H1, because a small fraction of the total H1 has been processed through disks. But it's the most highly clustered of the H1, right? Because it's the stuff that's like literally like fell into the centers of halos. And so that must affect this prediction though, because you're measuring both of those things. Yeah. And did your prediction, like how do your predictions, did your predictions just show that doesn't matter very much, or what?
We thought about that, but the thing is that like if you have K and PK, as you can expect that they will affect at small scales. And for SK-like experiments, it's very hard to look beyond K is equal to 1. So all those effects, they will actually influence the one bubble term, which is probably here, all this neutral hydrogen in the galactic center. But here we are mostly observing the large scale effect, as we are considering.
Meaning that even
like
at
5 megaparsec.
Even at this redshift, the H1 in galactic disk is not highly biased.
Mm-hmm. Yes.
Or not biased enough to overcome the fact that there's just so much more other H1.
Yeah, there are so like universe is filled up with the neutral hydrogen.
Yeah.
Now, if it is ionized, I will see its effect at large scales. But if I want to see the effect of the galactic hydrogen H1 neutral hydrogen, then at the power spectral level, they will change the power spectra at very high K. So very large K. At the small, it will have the small scale effect. But we did not include those effects. The reason is that SK-like experiment, they will probe the K scale till K is equal to 1. But these effects will probably dominate the short noise term, which is beyond K is equal to 1. So that's why we did not take into account this. But yeah, probably it will be nice to see that how the short noise term will change if I include these effects.
Whenever you do these like integrated line measurements, it's always a luminosity weighted bias. So the fact that the H1 in the disks is more clustered isn't nearly enough to overwhelm
Is it
just the
just like
luminosity
not
weighting
enough?
for being
Okay.
such a small fraction of the H1 that exists.
Okay.
Now, the last two things I want to talk about that what we are going to learn and why I'm excited about it. So one thing is that any measurement is better than no measurement. And if you look back like CMB like observations, for example, if we think that around 1980s when we were trying to do like people are trying to do the constants on cosmology using CMB, they did not even know that if they can see the higher order peaks at the CMB, which is very useful to constrain the cosmological information. Line intensity mapping experiments, in my opinion, are at the same level that any measurement can help us to rule out some of the models and also do cosmology in field. So particularly I talk about two unique cosmological probes that we can add the information from line intensity mapping and try to constrain those parameters. One is that the non-Gaussianity. So in cosmology we use it FNL to understand that how non-Gaussian this signal is, because ultimately the line intensity mapping observations are probing the large scale structure at different redshift in a large volume. So if I calculate the bispectra of any line intensity map, I'll be able to constrain this parameter, which is the non-Gaussian non-linearity parameter FNL. There are some forecasts which is very good to understand that what we can do, but of course if you change the models of astrophysical models, this forecast can change. And there are some paper like which says that we can constrain this FNL parameter to understand the non-Gaussian at the level of 1, which is probably super optimistic, but even if we can reach around 5, that will be, I think, interesting measurement to add up with the other complementary measurements like the constants from galaxy surface and so on. Another thing which can be done technically, that as it is probing the cosmological information, I can add this information into CMB and try to see that if it helps to improve all those cosmological parameters. One of them can be H naught. So it is done using the linear alpha forest at redshift 2.4. So as all of you probably know that there's a 4.4 sigma, maybe it's larger now, tension between the measurement of Hubble constant at high redshift from CMB and also the local universe, supernova measurement, there's a tension. Now if I can construct this parameter till a high redshift, it can add extra information how the dark energy evolves across the cosmic time, because people are considering about the early dark energy and so on. So this will be an interesting parameter to estimate from line intensity mapping observations. People have waited for gravitational wave observations to give complementary constant, but they need many more events. But whatever cosmological parameters we estimate from this from line intensity mapping observations, there will be always degeneration between astrophysics and cosmology, as I say.
For this H, is this a BAO based measurement you're imagining, or what is the handle you have on H?
Yeah, it can be simply measured using a Fisher forecast. So this line intensity mapping, if I observe it at redshifts z is equal to 6 and z is equal to 5 and z is equal to 3, I can see that how structures are forming. And this depends on the growth factor, which is proportional to this thing. So I can, if I marginalize over all the cosmological parameters, I can put some constant on.
Because you're getting it from D of Z.
D of
and
Z,
then,
yeah.
okay.
Because it's just simply structure formation.
Because you're, yeah, okay, because at that redshift, it's all matter anyway.
Some companies make BAO in full shape. Sometimes people put in these forecasts.
Yeah, there's some.
But you're talking about not shape, just amplitude.
Kind of can't do the amplitude because of that I² term hanging around.
Right, so it's not D of Z then. It's not the growth rate of structure that you're measuring.
Yeah, it's the shape.
It's
You
the
can kind of-
shape,
you
so
can
it's
kind
like
of
a
measure everything.
gamma, what we would have called in the old days a gamma measurement. It's
Yeah.
like the slope of the power spectrum. Okay.
I mean, it depends on how you marginalize over all the cosmological parameters, because ultimately I have one observation, which is the power spectra, and I know how this matter power spectra will behave if I change different parameters, right? Because this is sensitive to the small h, omega baryon, omega matter, and so on. So it depends how I take into account both astrophysics and cosmology, just to marginalize over all parameters. But whatever measurements we have, there will be always degeneracies between astrophysics and cosmology. And as we are into the regime of multi-probe cosmology, we can actually add different covariances from different observations and try to constant. So that is another direction which I am interested in. And last thing I want to talk about. So last thing I want to talk about that what I'm currently working on, that how to analyze this data. So I have written some power spectra code, because traditionally what we do here, which is unlike CMB, that CMB is a 2D measurement. So some of the things become a little bit easier to calculate, because ultimately I'm observing 2D noise and 2D signal. But here we have 3D signal. And it is okay to calculate the power spectra. For example, if the box size is 80 megaparsec, 50 megaparsec. So on. So it will be easy to calculate the 3D power spectra. But actually, in line intensity mapping observations, as we have the axis along the z direction, so ultimately I have more information, because the box will look probably 80, 80, 500, just I'm giving some random number. Now the question is that how do you want to analyze this whole chunk of data? So I'm basically writing my own power spectra code just to see that what can be the optimal estimator, so that we can extract more information from this kind of simulation box. So that is one other interesting thing, which is not probably helpful to probe the astrophysics, but just to check that what can be the optimal estimator to extract the data set. So finally, I want to conclude that it's very interesting in a sense that it's a very new field and also not very crowded like CMB. And there are a couple of things which we are going to look into, but ultimately the data will tell us what is the truth, in a sense that secret prime is scheduled to have first light maybe early 2025, so next year. It depends on how quickly we are assembling everything. But even if we have the first light mid 2025, within 2 years we can see some of the signals. At least it will be useful to see the signal at high redshift from C2 during the EOR epoch. And yeah, all of the things I'm interested in. So thank you very much, and I'll take happily take any other questions you have.
Other questions?
In the, the CMB, the goal in the CMB is to measure the power spectrum, but the foreground separation in the CMB is generally done in the linear, like in the image or in the ALMs or whatever, but not in the squares. They don't do it as a cross correlation. Of course, you don't have multiple CMBs to work with, so this situation is different. But it is, I've always wondered whether there's a way to think of this fact that you have the interlopers and you have multiple tracers. Is there a way to see it as a foreground subtraction before you do the power spectrum, or is it always the case that you're working with powers and you're decorrelating in the power space? I'm kind of asking, do you have to square first, or can you work with the unsquared data? Because you have this nice picture of this tube where you've observed That's what I want, you know, like I'm an old school astronomer. I want to look at the whole three-dimensional structure of the tube, not the square of the power averaged over K.
Yes, so, okay, here is the thing. So we can, I mean, I don't know much about how much stuff has been done, like CMB to work more on the component separation and making forecast. One thing could be to make templates that we do in CMB. We can make the templates from low redshift, synchrotron and dust and whatever, and then we subtract it.
Yeah.
So it can
Like component, that's a good word, component separation.
Component
People aren't really
separation.
thinking about it in terms of component separation, they're thinking of it in terms of like decorrelation. But I'm wondering if there's a component separation attitude you could take.
I don't know much about it, but one thing can be done as we are having the low redshift CO transitions. We can make a template of that CO and then subtract it from the to get insight at the high redshift. I don't know if it is done or not, but I was thinking about it, but I did not run all my simulations to do that.
There's a lot of questions about how you construct the template from whatever low redshift data you have, because kind of by definition you're predicting things, you're predicting galaxies you can't see. It's kind of the crude version of I think what you're talking about, the masking ideas.
I mean, the nice thing is that in this power spectrum space, it looks like your noise just comes in as an additive constant, and then that tells you.
That's exactly the reasoning. Whereas if you're doing the template, then it's hard to be sure.
But of course, not all noises come in that way. So anyway, I really would love
I
to
mean, masking can be
get into this.
one other way. One of our collaborators is working. But there I might mask some of the sources where I have also background C2. So I'm basically losing the signal also.
That's right.
But it depends. I think we need to compare all different technology, like algorithms, just to see that what is the highest fidelity we can have.
And some of the continuum component separation actually is happening even earlier. Some of it's happening at the time ordered data stage, like spectra from like a single 10 seconds of observation.
Right. Yeah.
Some of it doesn't even make it into that cube.
Right. Yes.
Other questions? All right, let's thank Anirban again. Figure out how to turn this off. Access the Oh, I know how to do it. I know what to do. I know what to do. I have to turn on the projector. Yes, yes, you're on my schedule.
And in the CMB, I really want to I feel like there's
Oh, I thought we chose a time. Maybe you're not on
like a
the
meta.
We didn't choose a time.
But I can't figure out exactly what it is. In the CMB, there's this thing, of course, where you want different frequencies to create a structure. And you know it has a particular temperature. I have to. And here you want to line recorded on a large scale structure. And I just have